Okay, so let's start lecture 3. Lecture 3. Fine. So, in this lecture, what we are going to introduce is the notion of directional derivatives. So, if I talk about a very basic geometrical intuition behind directional derivatives, of course, I can't draw a multidimensional space here up. But the thing is that if you are given, if you are given the curve, rather let me draw it in this way. I am trying to do it as much as I can. Suppose I have, some sort of this, says this is my z, x and y, and say I have, let's say I have a curve like this, okay, in the 3-dimensional space, and let's say I am assigning a vector, a certain direction to this. Suppose I choose a point here and I choose a vector here like v naught. So what I'm trying to do is that I am trying to construct the tangent plane at this point, okay, or rather in the I'm trying to construct a tangent plane in the direction of v naught. I am trying to construct a tangent plane in the direction of v naught, in the direction of v naught, sorry, not v naught, x naught, as I have chosen the point. And to calculate, and what I want to calculate is the slope of this tangent plane, the steepness. Calculate the steepness or slope of this plane. Fine. So this can be thought of as some geometrical intuition behind this, and a more layman terms we can say that the directional derivative is trying to linearize the function in a given direction. Like when you have a when you have a curve in a multidimensional Euclidean space, there are multiple directions around it. So if you try to linearize it, to approximate it with a linear function in some specific direction, that you can easily do. So that is something you can think of as directional derivatives. But that is this is a more more technical geometric process to think about it, that you are given a function and you are given a point x naught, then the directional derivative at that point in the direction of a vector v is just considering the tangent plane which includes the vector v in the direction of that vector passing through x naught and calculating the steepness of that plane. Fine. Okay, so without further ado, let's quickly define how a directional derivative works. So let E be a subset of Rn, and let f from E to Rm be a map. Let x naught in E be an interior point, and let v be a vector in Rn. Okay. Now we are choosing x naught to be an interior point, and we are choosing this direction. So this v will work as the direction. Okay. So we are choosing the direction in such a way that when I consider the vector, the very small vector which originates from x naught in the direction of v, that vector is still inside E. Okay. So this is something which we need to keep in mind, that we are choosing this vector in such a way that the small direction which we are assigning using this vector starting from x naught, that vector should still be inside E. So if the limit t tends to 0, t is greater than 0, and x naught plus tv, this small directional vector, is still inside E of this x naught plus tv minus f of x naught by t. This exists. Now something to keep in mind here is that the numerator is in Rm. Okay. So this is in Rm and this is just a scalar. So this division is well defined, right? We do not need to include the notion of norm in order to make this division well defined. So if this derivative exists, then we say that f is differentiable in the direction v at x naught, and we write the value of this derivative dv f x naught, this is the way we denote it, to be just the limit as usual, f of x naught plus tv minus f of x naught by t. Yeah. So the existence of a derivative in term of a with respect to a direction is, you can think of it as the existence of this tangent plane, okay, which passes through x naught in the direction of v, having this vector v inside that plane, okay, fine. Yeah. So this is sort of, now you can relate this to our one dimensional definition of a derivative. This is more analogous to to derivative in R. You can think of it like that, right? Because their purposes are quite similar. Here we are trying to calculate the steepness of a tangent plane, and in case of the functions from R to R, there we used to calculate the steepness of the tangents, right? So they are sort of doing the same thing, and hence they are carrying out the same representation, okay, fine. The several variable calculus is it seems to be quite complicated because it's quite difficult to visualize it. Like we can easily visualize real analytic things. In fact, it's some sort of easy to visualize real valued functions on n dimensional spaces as well. But once we have our codomain as a higher dimensional Euclidean space, it's some sort of very difficult to visualize, right? Okay, fine. Yeah. Now this directional derivative can also be thought of being calculated on the boundary of the surface or on the boundary of the set we are talking about, provided that these directional vectors, they are pointed inwards and not outwards, right? Yeah. That will actually give me the notion of what we call the left and right derivative in case of these multivariable cases. But something which you can immediately observation is that if f is a real valued function, then d plus 1 f of x is the right derivative, of f, clear, or f of x rather, if exists, clearly if exists, and similarly d minus 1 f of x is the left derivative, of f of x if exists, clearly, okay, fine. Yeah. Now we come to a very important sort of an observation which is very useful at this point, because in some sense we are trying to relate these notions of directional derivatives and these notions of total derivatives. Total derivatives was the one which we had defined in the previous lecture, because as we were talking about the Jacobian matrix, we will see that once we have the total derivative to exist, then we can, as I was saying in the previous lecture itself, then we can try and construct out a matrix which is the matrix associated to this derivative as a linear transformation, and this matrix will be completely dependent on directional derivatives, on some very specific directional derivatives. So they are interrelated in some sense, and that's why it is quite important to try and relate them, okay. So that's where this lemma comes into play, which says that let E be a subset of Rn, f from E to Rm be a function x naught be an interior point, of E, and let V be a vector in Rn. if f is differentiable, okay, so we are given all these setups for differentiability. So if f is differentiable at x naught, if f is differentiable at x naught, then f is also differentiable, then f is also differentiable in the direction of v at x naught. And what we have is the directional derivative in the direction of v at x naught of f is f prime at x naught, which is the linear operator which represents the derivative at x naught evaluated at v. Fine. Yeah. So what does this theorem specifically say is that if I have a function which is differentiable at an interior point x naught of the set on which the function is defined, then the function is also differentiable in the direction of some vector at x naught, and the relations between the total derivative and the directional derivative is given up here. Okay, let us try and prove this. Okay, what do we already have in hand? Okay, yeah, so any analytic proof comes with the fact that what do we already have in hand. Okay, so we already have that f is differentiable at x naught, right? Therefore I have that limit, so by the definition of limits itself, so I have limit x tends to x naught, x is not equals to x naught. So what do I have? Yeah, I have limit x tends to x naught, x naught equals to x naught. The norm of what do I have here? The norm of f of x minus f of x naught minus f prime at x naught, f prime at x naught operated on x minus x naught, this norm divided by the norm of x minus x naught is equals to 0, right? So this immediately follows up from the definition of derivatives, right? Fine. Okay. Yeah. Yeah. So now I need to prove that the directional derivative it exactly equals this, right? The f prime at x naught operated on v. Now observe that, so choose x to be x naught plus tv, or rather more relevantly choose this vector x minus x naught in the direction of v. Okay, choose x, what I mean to say is that choose x in such a way, or rather I think writing it in this way will be better. Choose x specifically to be the vector which originates at x naught and is in the direction of v. Okay, t is necessarily a positive scalar. Fine. Okay, yeah, because we are having a positive direction, that's why I am choosing t to be positive, right? If I choose t to be negative, then it will be conventionally backwards from x naught, that is not something we want. Okay, fine, this is something which we have here. Therefore I have, so now see, once x tends to x naught, t tends to 0, that's quite obvious here, right? Then limit t tends to 0 and we have t greater than 0 and x is coming from e, so this x naught plus tv is in e, right? Still we are in compliance with the directional derivative. And what do we have here? We have norm of here we have x naught plus tv minus f of x naught minus I have here f prime at x naught applied on tv, this is something which we have, divided by norm of t, and I have this to be 0, right? Now you can easily observe that I can take the norm outside here. Why can I do that? First of all, the norm is a continuous function, so it can be interchanged with the limits. This is something which we have studied previously in case of analysis, and that holds here pretty well in any metric space. Moreover, see, the reason we were choosing the norm inside of the limit was the fact that the division was not well defined, because the numerator was coming from some space and the denominator was coming from another space, right? But here we do not have that fallacy anymore. Here we have the denominator to be, a real scalar, right? So no more that complication. Fine. Yeah, so there's no more that complication. So I can choose it outside. So I have limit t tends to 0, t greater than 0. I'm not writing that anymore, and I have here f of x naught plus tv minus f of x naught by t. Fine. Now f prime x naught is a linear transformation and t is a scalar, so t will come outside. Once t comes outside, so I am writing is a t times f prime at x naught being applied on v divided by t, and this whole norm equals 0. But we know that this norm is a positive definite function, right? So this norm is a positive definite function, and the norm of something is 0. That means the vector itself inside is 0, and inside what we have, that's typically a vector in some sense, right? Because the numerator is coming from Rm, so this directional derivative should be an element of Rm itself, right? Fine. So this will give me limit t tends to 0, t greater than 0, f of x naught plus tv minus f of x naught by t, and these two t can be cancelled out. What is the reason? Since t is not exactly equal to 0. Okay, whenever we are trying to catch up with the limits, obviously that's the case. Minus f prime at x naught applied on v is equal to 0, and this implies that limit t tends to 0, or rather I can immediately use the shorthand form. The derivative in the direction of v of f at x naught is equals to the total derivative applied to fine. Therefore, now see, this actually gives us a lot of things, because this is a linear transformation. F prime at x naught, this notation is of a linear transformation, and whenever we are in some vector space, then we have representations of vectors in terms of linear combinations of basis elements, and the linear transformation behaves exceptionally well whenever we have a linear combination, because we can distribute the addition and we can take the scalars outside, right? One more consequence which you can immediately draw it from here. Yeah, so let me just keep it up here, or rather let me use a lighter shade. Let me use the red one. Fine. Or it's not looking good. Keep it high. Observation is that this immediately means that once a function is totally differentiable, it's directionally differentiable as well. Therefore, a function is total differentiable, that is, its total derivative exists, implies f is directional differentiable in any arbitrary direction. Fine, but the converse need not be true. Converse need not be true. Okay, why does the converse need not be true? Now this will be more clear once we have the Jacobian in hand, but for the time being I can serve an example. Suppose I choose this function r2 to r such that f of xy is given to be x cubed upon x squared plus y squared. Then, or rather you can work it out on your own. If you have studied, you have already studied, how to calculate total derivatives. You can argue on your own that f is not differentiable. F is not differentiable. Okay, I need to add something more. Okay, let me write it here. Okay, take f from r2 to r as, so f of xy, this is defined to be x, I need it to define to be x cubed upon x squared plus y squared if xy is non-zero, and it's 0 if xy is 0. Okay, then you can observe that f is not differentiable. F is not differentiable at the origin, but differentiable in every direction. Okay, now something which you can take up from here itself, that how to check whether a function is differentiable in every direction. Like you cannot you cannot possibly account for every direction because there are uncountably many directions, but what is the way in which you can do that? Okay. See, this vector which assigns us the direction, it is actually a vector from Rn, right? And Rn has a standard basis, fine. So something which you can observe is that now since V is in Rn, therefore I can write V as summation Vi Ei I is equals to 1 to n, where Ei are the standard basis vectors. But then what is the directional derivative of f at x naught in the direction of V? So it is just f prime, the total derivative applied on V, right? Fine. Yeah, so this can be written as the total derivative applied on the linear combination I is equals to 1 to n, and so this is nothing but, so the scalars will come out, each of these Vi's are scalars, so this is summation I is equals to 1 to n Vi times the total derivative applied on Ei. Now if, now I am, for the time being I am writing it immediately as the directional derivative in the direction of the standard vectors of f at x naught, right? Therefore if these exist, then we just need to check, so this implies that we need to check the directional derivative in the standard directions in the sense in the direction of the standard vectors, standard basis vectors, and these will account for existence of directional derivative in every direction, right? And we can account for the standard basis vectors because they are a finite in number, right? Whenever we have an n dimensional space, we have n of these vectors, fine. Yeah, so this actually makes things good. So now what we need to define is what is the derivative in the direction of these unit vectors. Yeah, fine. Okay, and that's what we call the partial derivative. So definition of a partial derivative. Okay, and that's quite important. So let me write it in yeah, okay. So let E be a subset of Rn and let f from E to Rm be a function. Okay, one thing I missed out here in order to make things a bit more clear. Let me go back to the, yeah. So this you can observe that this is nothing but the standard derivative which we use of f at x naught plus tv applied when t is equals to 0, right? Clear? Okay, yeah, this is a better way to observe things. Like, so if f is a real valued function, then this is far more better understanding. We will make use of this as well. This is better to calculate, it makes things easier to calculate, whatever. Okay, so f from E to Rm be a function, let x naught be an interior point of E, be an interior point of E, and let 1 less than j less than equals to n. Then the partial derivative of f with respect to xj, which is the jth component, of x naught, Okay, that is the point where we are calculating the derivative. It has n coordinates, right? Each of those coordinates basically correspond to uh, n different directions, right? That is the way in which we calculate the coordinates in a Euclidean space, right? We go via each individual mutually perpendicular directions, and each of those directions, the way the measure of the path traversed along each of those directions will give the coordinates. So the xj is the coordinate of the jth direction, right? So if I calculate the derivative in the jth direction at the point where we are calculating derivative, that's called the partial derivative in that direction. Okay, so in the jth component of x naught, denoted as del f by del xj, x naught is defined as, so what we need to do is typically is defined as, so here what should be the direction? The direction should be the jth standard vector, right? Because here, since we are calculating it in the direction of xj, and xj corresponds to the jth direction, the unit vector along the jth direction, right? So it is defined as del f by del xj, this is nothing but okay, of x naught, this is nothing but limit t tends to 0, t is not equal to 0, and x naught plus t e j is belongs to E. So what we have typically is that f of x naught plus t e j, so we are traversing in the jth direction, minus f of x naught upon t, and the better way to write it as is d dt of f at x naught plus t e j calculated when t is equals to 0. Okay, provided the limit exists, clearly provided the limit exists. Fine, clear? Okay, one more thing, sort of a notation, we say that f is continuously differentiable, f is continuously differentiable at x naught if each del f by del xj at x naught exists and are continuous on. Fine. Okay. Now something which you can immediately observe is that now this function which we had chosen was a function from E to Rm. E was in Rn, right? So by definition, this directional derivative del f by del xj at x naught, this must be inside Rm, this must be a vector in Rm, so it must have m coordinates. Okay, so the thing which you can quite easily observe from exactly the definition of del f xj, because how are we calculating the partial derivatives? To calculate the partial derivatives, we are just choosing the unit vectors. Once we choose the unit vectors, it becomes component wise, right? Clearly if f equals to f1 f2 till fn, because it is in Rm, the function f, so what I mean by f is that f at some point, some arbitrary point, okay, then the directional derivative in the j direction of x naught is just the directional derivative of each of these components, and so on. Okay, so it is similar to take, now each of these fi's are real valued functions, right? Each of these fi's are real valued functions, right? And here the symbol which we used, that d dt, yeah, so this will be well defined once we consider the components, right? So therefore we can observe that to differentiate a vector valued function, one just has to differentiate the each of these components of that function. Is it clear? Yeah. A quick example, let f be a function from R2 to R2 such that f maps xy to x square y square, then let's say, see in an arbitrary case, what is del f by del x? So here the components are x and y. So you just not need to get confused with the way we had defined it. We had defined it in terms of xj's, but in that case conventionally we have considered each of the components to be indexed by these j's. If the components are of the form x, y and z, then our partial derivatives will just be del f by del x, del f by del y and del f by del z in that form. So what is del f by del x? So this is basically del f1 by del x. So this is my f1 and this is my f2. So this is del x of x squared, del x of y squared. Y is obviously independent of x, so this is just 2x0. Similarly, my del f by del y will be 0 to y. Fine, at any arbitrary point. Clear? Okay. Fine. And the other case we have now we have already observed that if each of these partial derivatives exist, then the derivatives or rather we can say that if a function is differentiable, is totally differentiable at some point x0, then all its partial derivatives will immediately exist because all its directional derivatives exist, right? Fine. One more thing, so let me go back and let me come to the from here we can continue this writing in this way also. We can say the directional derivative of f in the direction of v at x0 is nothing but sum of the linear combination where the coefficients come from the coordinates of this vector v equal to 1 to n, for example, times the directional derivatives of f at x0 in each of these j directions, right? Thus the directional derivatives can be completely characterized using the partial derivatives. Fine, clear. And when is it so? When it can be defined? So let me just quote unquote that therefore one can define directional derivatives in terms of partial derivatives, but to define it in terms of partial derivatives we made use of the fact that f prime at x0 is a linear is a linear transformation. Therefore f prime at x0 need to be existing, right, provided that f so one can define directional derivatives for f is totally differentiable at x0. Fine, okay. Yeah, and the converse need not hold here as well, that if a function is partially differentiable at some point x0, then it needs to be totally differentiable at that point x0. So if that's quite intuitive at this point, if f is, you can choose the same function as we did previously, x cube by x square plus y square whenever xy is not 0 0 and exactly 0 when xy corresponds to the origin, then that will be differentiable in every direction, correspondingly in every direction of the standard vectors, but it's not differentiable at the origin. So if it's partially differentiable does not imply f is totally differentiable. So partially differentiable at x0 does not imply it's totally differentiable at x0. Totally differentiable at x0. Fine, right? Therefore we need to have some characterization because we have worked a lot to define these partial derivatives, and if I cannot have any sort of a converse then it's sort of very weak, right? So in the next lecture we will study that provided a function is there such that all its partial derivatives exist, what should be a condition applied to it such that we can assure that f is differentiable as well. Fine, yeah. So that is the topic for the next lecture. So meet you guys there.